All right, folks, welcome to the last chapter of the semester here. For GO 100, this is chapter 10. For GO 111, this is chapter 13, all about climate change. And I know in the last several videos I haven't been playing a lot of the YouTube videos and clips in there, but I will be playing them with this one just for dramatic effect and all that jazz, right? So, without further ado,
climate change is the 800-pound gorilla in the living room that the media dances around. But in the scientific community, it's a settled question. 95% of scientists believe that it's happening. Temperatures are rising. With 90% confidence, we believe it's human activity and not natural cycles that is driving the increase in temperature on the Earth.
We have to find a balance within reality. Focus on longevity rather than a salary. Globally, we need to stand up to these factories and make the switch from combustion to batteries. It's sad to see something die when you water it. They say they monitor pollution and it's moderate, but take a look at the sky by your metropolis. It's being poisoned by people in your populace. It's a wake-up call for all the ignorant folks who don't understand until the back's pinned to the ropes. Your vision of hope flips like fishermen's boats. I hope you're listening close because the system is broke. I see fire and smoke billowing from refineries and wonder why it's accepted by society. These two circles in my skull don't lie to me. You must survive then thrive. This is irony. How much longer can we keep doing this? This is the stupidest thing we could do. Tell me I'm wrong with this. Isn't it obvious? We're all doomed unless we change soon. How much longer can we keep doing this? This is the stupidest thing we could do. Tell me I'm wrong with this. Isn't it obvious? We're all doomed unless we change soon. We put man on the moon back in '69. We have unmanned drones that can roam the sky. We can transplant hearts, there's a rover on Mars. So what's the hold up with electric cars? The truth is, these cars are bad for biz. Oil and gas collect cash hand and fist. Why can't electric be cost effective? It feels like I'm eating gas fumes for breakfast. All you gotta do is take a look at the ice caps. Anyone can see that they're melting quite fast. We keep pumping all this crap in the atmosphere, then act confused when the weather starts acting weird. Honestly, a lot of it's economy and politics. If you don't believe me, ask a climatologist. The earth is more than just countries and continents. Sometimes I wonder what we really have to offer. How much longer can we keep doing this? This is the stupidest thing we could do. Tell me I'm wrong with this. Isn't it obvious? We're all doomed unless we change soon. How much longer can we keep doing this? This is the stupidest thing we could do. Tell me I'm wrong with this. Isn't it obvious? We're all doomed unless we change soon.
What now has to be done to make things better?
Global warming is happening and man's to blame.
You can see where the tension is now between the science and the politics of carbon and carbon generation, which literally is causing climate change and the warming of the planet.
Thunder and lightning, Mother Nature is frightening. The giver of life, beautiful and enlightening. We must unite as a planet and do the right thing, or be prepared for the damages that we might bring upon this starlit, marvelous creation that spun more than 4 billion sun rotations. We're playing a game with what we don't understand. In my mind, it's unwise to bite the hand that feeds you, gives you fresh air to breathe through, clean water to drink, wash clothes and clean you. And what do? We poison the seas, the lakes, the rivers, and destroy the trees. We pollute the air and the ground beneath, all for the economy, wealth and greed. Well, tell me, how big will your company be when your grandson's grandson has nothing to breathe? How much longer can we keep doing this? This is the stupidest thing we could do. Tell me I'm wrong with this. Isn't it obvious? We're all doomed unless we change soon. How much longer can we keep doing this? This is the stupidest thing we could do. Tell me I'm wrong with this. Isn't it obvious? We're all doomed unless we change soon.
In the last 10 to 15 years, the extent of awareness that's grown has been quite phenomenal. And therefore, I personally feel that there's every reason to feel that human society will have the sense, the wisdom to exercise their characteristic of risk aversion and see that we do the right thing and do it in the right period of time.
all right, Uncle Adams, everybody. Folks, I'm not quite as optimistic as that gentleman at the end there. But as we talk climate change here, whoops. So let's take a look. These are just some selected climatic anomalies and events that happened in 2017. I'm not going to raid through all of them here. You can take a look on the online if you want. Here's 2018, right? Here's Hurricane Florence, Hurricane Michael, right? Here's 2019, Hurricane Dorian, right? Now, the point here is, now these are all significant climatic anomalies, but is any one of these, or kind of, a bunch of these taken together, is that evidence of climate change? And the answer is no, of course. It's evidence of what? It's evidence of weather, right? These are all weather phenomenons, right? So, but climate change, right? It's not, you hear, oh, well, it snowed in Florida, so climate change is obviously bogus, right? Well, no, it's not climate, that's weather, right? Climate is the long-term trends in a region, right? So any one of these together is not, evidence for climate change. But when, unusual weather patterns like these are no longer unusual weather patterns, that, folks, is climate change, right? And I'd also like to point out that what I'm going to show you a lot in this chapter is all the data, right? So remember, way back till the beginning of the semester, we talked about the science and scientific method, right? Now, what I'm going to let you know here is climate change, folks. It lies in the data itself. You don't have to come up with a hypothesis and run it through the scientific method and experiments, right? Climate change, folks, is in the data. If you tell me you do not believe in climate change, what you are literally telling me is you do not believe that 3 is a bigger number than 2. Right? So what I'm going to show you a lot today is different data, and here's some data, right? Here's 2018. This is $1 billion disasters here in the United States, right? Each of these cost us more than $1 billion. Here's 2019 billion-dollar disasters, lots of floods in the rivers, right? California wildfires, Alaskan wildfires, right? Hailstorms in Colorado, all of these, right? And again, just taken, by themselves, these are not, evidence for climate change. Climate change is going to be long-term trends. So let me show you some of that data, right? Here is some data. Top 10 warmest years since 1880. Notice 2019, second, 2016, 15, 17, right, 18. You'll notice that all of these are in the mid to high 2000s, right? Now, this is a long-term trend. This is data on climate change, right? Here's some more data looking back to 1880, looking at decadal averages, which means, you take the temperatures of the whole decade and kind of average them out. So we notice the 1880s, and this line here is kind of the, from the average of 1880 to 1980, I believe. But what you see here is, we started off 1800s, late 1800s, early 1900s. It was a little cooler, right? Not sure what happened here in the 1940s, right? But then as we get into the 80s, you'll notice from a lot of this data, the 80s is when we really start feeling some of that, the effects of climate change. And the 1980s, right? The 1980s is the warmest decade on record at that time, right? That is until the 1990s. Then the 1990s became the warmest decade on record at that time. Every single year of the 1990s was warmer than the 1980s average. Then that trend continues, right? So here are the 2000s, right? So every one of the 2000s, right? Every single year, 2000 to 2010, right? Is that's now the new hottest decade on record, right? But then every single year, importantly, every single year in the 2000s warmer than the 1990s average, right? And the data isn't out for this decade yet, but you imagine that trend may just continue, right? Let me show you some more data here. Now this is satellite data from starting in the 1950s, let me just pause this a second here. So what we're seeing, right, we'll go back to the 50s here. Right. What we're seeing is, here's the average, 1880 to 1970s, I believe, average, right? But what we'll start to see here, so this is satellite data, right? So this is just information telling us how much warmer it's getting. Let's watch as we play this here, right? 60s, 70s, here come the 80s. Now we can really see how we're starting to feel it, right? Especially up near our poles, 2013, right? That's about where that one ended. Whoop. Let's do that again. 1950s, 60s, 70s, 80s, 90s, 2000, right? 2013. So let's take a look here, right? So now we can see this trend of increasing temperature globally, right? Notice our poles, especially our North Pole here, is especially affected by that. And a lot of our polar regions are especially highly affected by climate change, right? Lots of melting sea ice. Remember, right off the coast of Greenland here, this is where the primer for our deep water circulation, our thermohaline circulation, begins. So now what I'd like to show you, is the new Arctic report card for 2019, and I have actually not watched this yet, so we'll watch this together for the very first time here. See how well we did in 2019.
Unprecedented warming and exceptionally low levels of sea ice are imposing dramatic, rapid, and disruptive change on marine ecosystems in the far north. The Bering Sea has been nearly ice-free for 2 winters in a row. The warmer water has caused marine species to move farther north, impacting vital commercial fisheries and indigenous subsistence harvests. There has been a cascade of impacts on the marine food web, from microscopic creatures to large marine mammals. Massive die-offs of seabirds and other animals were seen. This years-long pattern of climate warming and ice loss in the Arctic is likely to continue, threatening ecosystems and livelihoods with far-reaching global implications. The loss of ice, snow, and permafrost in the Arctic is causing damaging changes to the northern landscape. In 2019, the Greenland ice sheet continued melting at a dramatic rate. This will inevitably contribute to widespread coastal flooding in the years to come. Thawing of permafrost ecosystems in the Arctic is now releasing carbon to the atmosphere at a rate of up to 600 million metric tons per year, accelerating climate change. Changing growing conditions, including warmer summers, decreasing snow cover, and permafrost instability, lead to alterations in the vegetation of the Arctic landscape. This can strongly affect habitat for caribou, birds, and other wildlife, putting further pressure on northern ecosystems and communities. Indigenous communities along the Bering Sea are on the front lines of climate change. As sea ice disappears, so does hunting access to seals, whales, walrus, and other marine life.
There's less and less snow, and there's less and less ice. And that means trouble, not only us hunting and fishing, but the animals that we depend on.
We're seeing a lot of birds die off every summer. It's really gotten worse within the last 5 years. The lack of ice really hurts our food chain.
More open water exposes shorelines to storm surges, flooding, and increasing erosion. Despite the stresses of climate change, resilience is also a way of life for the region's indigenous peoples.
There's a lot to protect today before a total disaster happens.
Yeah. All right. Hopefully you're report card's a little bit better than that, right? All right, so we're not doing too well, right? And one of the big issues in our Arctic, right, is the sea ice itself, right? Now, I've mentioned this before in class, one of the big deals or big differences between ice and liquid water, right, the cryosphere and the hydrosphere, is it acts completely differently in our systems. And one of the way it acts completely differently is what's called albedo, and that's reflectivity of the surface. So ice, right, white ice, white snow, reflects almost 100% of the sunlight energy that hits it back into space, whereas open water absorbs almost 100% of that sunlight energy, right? So when sunlight energy hits open water, it absorbs it, it warms up the water. When the water warms up, it causes ice to melt. Less ice means more open water. More open water means more of that radiation is going to hit the water and be absorbed by the water, which leads to an increased rate of temperature increase, which leads to an increased rate of ice decrease, which leads to an increased rate of temperature increase, which leads to an increased rate of ice decrease, yada yada, right? And of course, like we mentioned, before, and we've been touching on throughout the whole semester, is that all of these different parts of, our climate system and geology, everything's all intertied. It's all open. It's all interacting with each other, right? And perturbations in one system can cascade through the other, right? And of course, when we're talking climate, right, it's very multidimensional. We got the atmosphere, the hydrosphere, the geosphere, the biosphere, and then the cryosphere, the ice and snow, again, separated out for one of the reasons that it acts completely differently in how it absorbs or reflects sunlight. Right? So, and we've mentioned this before too, climate impacts many geological processes, right? Weathering, flooding, mass wasting, these are all highly impacted by climate, but geological processes also affect the climate, right? Large volcanism, we've looked into that, right? Can change and alter climate over the planet for a number of years, right? Mountain building can disrupt surface or wind circulation patterns. The position of the continents changes oceanic circulation patterns, all this kind of stuff, right? So how, as we look back in the past, right, do we find this data for climate change, right? So first of all, we can use, obviously, instrumental records, and by that I mean a thermometer, right? And these only go back, however, a couple centuries. Now we've had thermometers for a long time, but, daily records or, yearly or whatever records, these only go back a couple of centuries. Beyond that, we have to use proxy data through a science known as paleoclimatology, and paleo simply means old, climatology, climate. This is the study of ancient climates, right? So we reconstruct these ancient climates using proxy data, which is indirect data, evidence of change that we can see, but indirectly, so we're not, taking a, thermometer and getting direct measurements, right? So here's some examples of that proxy data. Seafloor sediments themselves, this is a vast storehouse of climate data, especially little microscopic marine organisms and all sorts of marine organisms, right, are very sensitive to temperature and salinity, right? So finding these in certain areas can give you a clue as to what temperatures were around while those guys existed, right? Oxygen isotope analysis is another one, right? Now isotopes are different. They're the same elements, but they have different numbers of neutrons, right? Remember way back to the beginning again, if you change the number of protons, you change what element it is, but you can add or subtract neutrons and keep it the same element. So oxygen isotope analysis, looks at these different isotopes of oxygen and can analyze temperature from that. Right? And then climate change, we also have ice cores, glacial ice. We have a record going back 800,000 years. Now, not from one ice core, but we can take this ice core and match it up to this one and that one and that one. And we can build back a record, almost going year by year back 800,000 years. And the nice thing about ice is, what gets trapped in the ice. You also get, pollen and little air bubbles that get trapped in there. If you stick a microprobe into these air bubbles, you can directly test the ancient atmosphere, right? Volcanism, you can get ash layers, all this kind of stuff that really helps to determine climate, right? Tree rings as well can be used not only for dating, but they can, stores environmental history of what climate was like while that tree was alive, right? And in the southwestern United States, we can actually take this back several thousand years. Some other types of proxy data we have: fossil pollen spores, corals, right? And then historical data. And historical data is different than instrumental records. Instrumental is a thermometer. Historical data is more like, oh, the blizzard of '06 was so bad, all my cows done froze, that kind of thing. Right? So here is a look going back to 300 AD here, using these proxy-based, those are the black ones, right? And then thermometer-based records going back to, the mid-1800s or so here, right? And these thermometer-based records in red here, right? Notice they don't have these kind of extra lines about them. This is the uncertainty. It's, if you're a statistics person, it's a 2 phi standard deviation. Anyway, but the uncertainty here again is, of course, because there's a little bit of variability, within, when you collect CO2 or fossil pollen, right? There's a little bit of temperature range or variability that could exist. So this is the average, and this is, the likely, right? Now, why isn't this uncertainty around our thermometer-based instrumental records here? Well, it's because, you're just reading it directly off the thermometer. There is no uncertainty with that, right? So, looking at and starting to think about the greenhouse effect here, let's look at our budget of solar radiation. It's often the budget of solar radiation that affects, whether we're in an ice age or an interglacial or whatever, right? So let's look at some of the paths of this energy coming in. So about half of the solar radiation, right, passes through the atmosphere and is absorbed by our planet, either by water or by land, right? About 20% is absorbed by the clouds in the atmosphere, right? But clouds are also white, so they also reflect some of this, right? So some of this is reflected back, by backscattered to space. Some is reflected off the clouds. Some is absorbed off the clouds. And then some is, reflected off different land surfaces, especially snow and ice. Now, the difference is this solar radiation that is incoming is shortwave, high-intensity solar radiation, right? When this is absorbed by the Earth or the clouds, it is then used to heat up the Earth, right? And then the Earth re-emits a different type of radiation. And this is the big difference here. This is a long wave radiation. It's much lower intensity radiation, and this is the stuff that can be absorbed and then re-emitted by these greenhouse gases back towards Earth, right? So the long wave radiation heats the atmosphere, right? Some of it escapes back into space, right, here on Earth, and then some of it gets bounced back via the greenhouse effect, right? So this shortwave incoming solar radiation passes through the atmosphere, heats the Earth, right, or the body, right? So let's take a look at airless bodies like the moon here that doesn't have an atmosphere, right? So incoming solar radiation, right? This is the shortwave. It heats up the moon, and then the moon re-radiates long, lower intensity radiation back into space, and of course without any atmosphere or greenhouse gases to trap it, it all escapes back into space. Here on Earth we do have an atmosphere, right? So again, incoming shortwave solar radiation are absorbed by Earth and re-emitted as long-wave low-intensity radiation. Some of this is absorbed by the greenhouse gases and re-emitted back towards Earth, or some of it just escapes, back into space as well, right? Now, here's an example of Venus. Venus is an example of a runaway greenhouse effect, essentially, right? It has an atmosphere, a very thick atmosphere. It's not that much closer to the sun, really, that it should be any different temperature-wise, that much different temperature-wise from us. But it does have this runaway greenhouse effect. So you get the incoming shortwave high-intensity radiation, heats up Venus, right? Now low-intensity short or long-wave radiation is re-emitted. Almost all of that is trapped and then re-emitted back towards Venus itself. So it's basically, you know, just trapping all of that heat that's coming in. All right. So let's take a look at our impact on this process, right? So by modifying the land, we have ground cover that has been altered, right? So clearing and clear cutting, right? This is removing trees, which actually absorb and temporarily sequester some of this carbon, right? Overgrazing also alters this, right? And then changing the reflexivity, evaporation rates, and surface winds. So cement and, you know, sidewalk and that kind of stuff is, you know, fairly light colored. It's going to reflect a lot more. Or is going to absorb actually a lot more, right? And then losing sea ice is changing the reflexivity in the Arctic and leading to ever increasing temperatures and ever decreasing sea ice, right? How have we been modifying the atmosphere? By adding greenhouse gases, right? Carbon dioxide, right? By burning fossil fuels, deforestation, and then, you know, melting now of permafrost, as we just heard in that video, right? So taking a look over the last now 600,000 years using proxy data, right, and then in the last couple of hundred years, you know, just instrumental record, right, CO2 levels are now the highest they have been in the past over 600,000 years, possibly up to 3 million years, right? So here we see our trends, and I showed you this when we talked glaciers, right, but as we look here, right, when CO2 has this unique correlation with temperature, and that is that CO2 tends to track temperature. So when you have higher temperatures, you have higher CO2 levels. And it looks like naturally the temperature is forcing the CO2 levels, and the big reason for that is CO2 is often a byproduct of chemical weathering. So the warmer the temperatures, the more chemical weathering, the more CO2 is released, right? But now the interesting change is that now it is our CO2 levels that are currently forcing our temperature. You catch that? So throughout all this temperature, all this last 600,000 years, it's been the temperature that's been forcing the CO2. Now in the last 100 years or so, since the Industrial Revolution, it is the CO2 that is forcing the temperature. We're not still feeling the effects yet of all this temperature and all this CO2 release. It takes a while. You know, there's a lag time between when you release it, right, and then when you really feel the effects. And so taking a look here is CO2 concentrations, which again, when CO2 is high, temperature is high. When CO2 is low, temperature is low, right? So here we see our history of our ice age. Remember, we're still in an ice age. There are two stages to an ice age, a glacial stage and then an interglacial stage, and we are currently in one of these interglacial stages, right? And so what we see here's the last glacial stage. Temperatures and CO2 is low, interglacial, high, CO2 low, glacial, interglacial, glacial, interglacial, glacial, interglacial, right? And what we're seeing here is over this, you know, past 600,000 plus years, it was CO2 never was higher than 300 parts per million, right? Until, you know, this last part of the decade. We are now, folks, hovering right around 415 parts per million CO2. And again, the big deal about that is now it is the CO2 that is forcing the temperature, right? So let's look at some of these impacts that we have had on climate. First of all, global temperatures have increased in response to this increased atmospheric CO2, right? Again, this CO2 now forcing the temperature. That's not how it normally is, right? So in the past century, we've increased, 0.8 of a degree centigrade, which doesn't sound like a lot, but it really is, right? The warmest 16 years ever since 1980 since 1850 have all occurred since 1995, right? This is all, again, just data, folks, right? Here, this is projection. So this is, you know, a scientific model now, projecting and modeling how this might occur out into the future, right? So temperatures are expected to continue to rise in the future, of course, and the amount of this increase is really dependent, you know, on how good a doobies we are, right? If we really take dramatic action to slow our output of carbon, right, we may, you know, see more one of these lower line trends, right? But if we do nothing, and here's our current kind of trend here, right, we're going to see even higher and higher changes in temperature, right? You know, one of the things to realize here, now this is all scientific modeling, right? So it uses, you know, our best data that we have, but, you know, it's only as good as the data you put into it, right? So what I want to show you now is a history of CO2 on our planet. And it's going to take just a moment to orient you to this graph here. So let me show you what we got going on here. All right. So here we have the CO2, right? And each of these dots is a different reporting station. If you look here, we have 90 degrees south to 90 degrees north. So this is the South Pole. This is the North Pole. It's like the Earth basically tilted on its side. So here's our blue dot, right? That's the South Pole. And then here, this red dot, this is the Mauna Loa Observatory, a climate observatory that's been in, you know, in action for quite a long time. And then all of these other dots are other stations reporting in between there. So what we see is basically from the South Pole all the way up to the North Pole, this trend in CO2 change. So what we'll notice here, this is 1979, right? So these, again, folks, these are all data points, right? This is not run through the scientific method or anything. Okay, I will give you this, right? The lines drawn between these points, that's interpolation, right? Just draw a line between the points, right? But as we see this go on and get later, you know, more and more recent years, you'll see more and more of these stations reporting. So this interpolation becomes less and less between each of these stations, right? So what we see here is our parts per million CO2, right? What we see here is our clock, what date it is. These are the stations that are reporting. And then we're going to look at our global view temperature plus CO2, right? And this is going to show you, you know, our kind of rise. So starting in 79 here, remember, like I said, it's in the 1980s that we really start to feel a lot of this effect. I'll start playing this here, right? And you'll see there's a lot of seasonal kind of variation. The South Pole holds pretty steady, but there's a lot of seasonal variation here, right? We're noticing, so here's our CO2 line, here's our temperature trend, right? Global view, right? Going back, now we're in 84, right? We're in 40, right? 86. Right. October 1989, 350 parts per million for the last time, seen at Mauna Loa, right? Coming up to 93. Oh, we're coming up to the 2000s. I don't know if we're going to make it up to 400, folks. I don't know. We got a long ways to go here. Let's see. Look how many stations are reporting now, right? Interpolation's a lot less, right? See some kind of crazy spikes going off, but then they kind of taper out, right? We're looking at averages here, right? Oh man, 2000s. Are we going to make it? I don't know if we're going to make it up to 400. I think we only got till 2016 on this one. Oh, only 10 years left. I don't know if we're going to make it, folks. Notice our steep upturn, right? 2008. I don't know. It's going to be close. Only 6 years left. Come on, 400. Come on, 400. You're going to make it. 1 year left. Yes, we made it. Oh, wait, that's a terrible thing, right? Sorry. So, let's take a look here. Now we're going to go even farther back into the past, into the 70s, right? We're going to go through 58. This is another, these are record data, right? So, we're looking at here different records, right? Now, going back past this, we're going to use ice cores, right? So this is the Law Dome ice core. And remember I said we can use these ice cores, right? But we don't have one that goes back 800,000 years. We go through a couple different ones, right? So this is the Law Dome ice core. Now let's look. We're going to go to a different ice core here, all right? This is the Vostok ice core, all right? Looking back even farther. 440,000. So here's interglacial, here's a glacial period, right? 60,000, 80,000. Should be coming to an interglacial pretty soon. There's an interglacial period, right? Glacial period, interglacial period, right? Glacial period, right? Interglacial, glacial. And then now we're on the Epicodome sea ice core, right? And we see those glacier, interglacial, glacial, interglacial, right? So what we should be noticing here, right, is that this is really our current CO2 levels and trend are really unprecedented throughout the history, even of our ice ages, right? Yeah, we have interglacial and glacial, and the temperature keeps fluctuating, but this is unprecedented even throughout the history of our ice ages, right? So, folks, we'll pick up next time with part 2 and finish off the semester with a discussion of, the rest of climate change here.